So the team project you're going to work on this semester is a project that I call Market It. And it's a project in which you're given a fictitious set of test marketing data for a new product. And this is a product that you and your fictitious company are going to have temporary monopoly power over in the market. So you have no competitors. It's an innovative product like nothing else out there. And your marketing team has done some test marketing data, and you have to figure out, based on the data that you've collected from the test markets, and based on the cost of production data that you also have from your fictitious company, figure out how to price your product, how much of your product you can expect to sell in order to maximize the profit that you make in the process. So that's what this whole project is about, is maximizing profit, which seems like a sort of a smart business thing to do. And it's arranged into these 5 different decision points. And the first decision point is called sizing the market. In sizing the market, we're going to take the test market data and try to extrapolate from the small test markets out to the bigger national market for your product. The second decision is the demand function decision. It's where you're going to actually come up with a formula for a best fit function to model the demand for your product, the relationship between the price you want to charge and the quantity that you will sell on the national market at that price. The third step, the total and marginal revenue step, you build that demand function into a revenue function and begin to explore some of the properties of the revenue function, the relationship between the quantity that we sell and the amount of sales revenue that we take in from those sales. Finally, so far up until that point of the project, you've completely ignored the costs of production, which are pretty important. And so step 4, you take those costs into account as well. And when you consider both revenue and cost, how do we maximize the difference between the two, the money that's left over after we have paid to produce and then also made money by selling a certain number of products? How do we maximize that profit? That's step number 4. And step number 5 is a sort of a step further, which is to say, now that we've decided on the price we're going to charge in the national market, how much money have we potentially left on the table because there were people who would have been willing to pay more for my product than we're actually charging? And can we dip into that, what's called consumer surplus, through a scheme of price discrimination, and sort of what could we expect to result from that? So that's the overall shape of the project. Now let's look at each one of the steps and what the mathematical shape of each one of those steps looks like. So this project was originally developed out at the University of Arizona. And the data files that were generated in this project give you, first of all, some test marketing data. So this particular data file has had a product which is marketed in 6 different test markets. This is a common thing to do in marketing, is you go to some small markets out in the country, you set a price point in each market, and you go and do the research and figure out how many sales would we expect to get in, Biloxi, Mississippi, if we tried to charge $265 a piece for my product. How many sales would I expect in Peoria, Illinois, if we charged $310.95, right? And so in each one of those test markets, you gather some data. So you'll have a certain number of test markets of various sizes, numbers of consumers in your market, various price points that you tested out in those markets, and then how many sales you would have expected per year at that price point in each of those test markets. So the first step in the project is going to be to figure out how to scale up each of these small markets into the size of the potential national market for your product, right? What can I learn about how many sales I would expect among a market of 350 million people based on how many sales we discovered in a small test market of only 144,000? So this is just an exercise in proportional reasoning, scaling up the values of my market sizes and my market sales from the small market size to the national market size. If you're using Excel, and I recommend using Excel for this project, the easiest way to do that is just by figuring out, first of all, how much larger than the test market is my national market. So 350 million is how many times larger than 144,900? Well, that's just the ratio, 350 million divided by 144,900. Okay. So what this number is telling me is that the national market is 2,400 times as large as this small test market was, right? That's what that ratio tells me. And so, therefore, on the national market, I should expect to see, all else being equal, 2,400 times as many sales as we saw in this small test market. So the national market demand, the amount of quantity I could sell in the national market, is that number multiplied by the number of sales, multiplied by this 570 that we saw in the test market. Okay. So I would expect to sell 1,376,811 units on the national market. To make the units tractable in this problem, we like to have the national demand measured in thousands of units. And so that's going to be what we call Q, my demand quantity. So to get this number in thousands, I just have to take it and divide it by 1,000. So that now 1376 means that we have a demand of 1,376,000 units. I do this same thing for all of my various test markets, and that's going to give me my relationship between price, unit price, and quantity. So this is going to be my X values. These are going to be my Y values for my demand function. Because in my demand function, the price is a function of the quantity. P is a function of Q. And so that's where the algebra part of the project begins. We started with all this test marketing data. We figured out what the nationwide expected demand is. And we can plot those points on a scatter plot, right? And they're going to show this decreasing trend. Because, of course, if we want to sell more of our product, all else being equal, we have to set a lower price point in order to do that, right? And so we will have a decreasing function, which is our demand function, the relationship between price and quantity. And so in decision report number 2, we want to find a function that fits that demand data as best as possible. And we're going to, for the sake of making our calculations easier, the kind of function we're going to use to model this demand is a quadratic function. So using either Excel or Desmos or whatever your preferred tool is, you'll find a quadratic function, so a parabola of best fit, if you like, that goes as close through the data points as possible, right? And that demand function is where the algebra part of the project kicks off. So in my example, d of q equals this quadratic function that I see above me here. That's the quadratic of best fit for the data. I'm going to recommend that you round off your coefficients to 3 significant figures. So see how I have 2, 6, 8. The first 3 non-zero digits that I see going from left to right are going to be the ones that I stop, just so I don't have to keep too many digits in my calculations. Okay. So decision report 2 sees you fitting this quadratic model to your demand data. And then once you have that quadratic model for your demand data, you can figure out your sales revenue. The sales revenue is nothing more than the product of price times quantity. How much money do I make from sales? Well, I make exactly as much as the unit price of a single sale multiplied by the total number of sales at that unit price. Price times quantity, right? And so from the level of algebra, we do that just by multiplying the demand function, d of q, by the price. The demand function is the price. We multiply that by the quantity, which is q, to find out the revenue function. So we just multiply d of q by another q to get my revenue function, which looks almost exactly the same. It's just that all the powers of q are 1 higher in the revenue function than they were in the demand function. Right? There's another interpretation of revenue on my demand graph that we can come up with as well, because it's price times quantity. And on my demand graph, quantity are my horizontal measurements and price are my vertical measurements. That means that when I multiply a price times a quantity, I'm multiplying a width times a height on my demand graph. And width times height is otherwise known as area of a rectangle. And so one way to understand where to see revenue on my demand graph is once I have picked a price, let's say I want to sell this product for let's say I want to sell 800,000 units of this product, so my quantity is 800. I would have to set a price according to my demand function of about $264 per unit. Okay. And at that price and at that quantity, the amount of revenue that I'll make is 800 times 264.42. It's the area of this green rectangle. And because the revenue numbers are going to tend to get fairly large, okay, we want to measure revenue in millions of dollars instead of thousands, and so we're going to divide by 1,000 yet again when we come up with a revenue function, just to make the numbers a little bit easier to look at. Right? So the area of this green rectangle here on my demand graph is the revenue that I would get from selling 800,000 units of my product at $264.42 per unit, which when I multiply those together, I get about $211 million in sales revenue. Okay? So each of the rectangles that we can inscribe underneath my demand function here gives us the amount of sales revenue that we would make at that price and at that quantity. And what you might notice about the revenue function is that it has a maximum, right about there or so. So that revenue function will max out. It will reach a highest point. In this example, looks like right around 640 units of sales or so, right? And so decision report 3 is going to be about building that revenue function, both algebraically and then also investigating some of its differential properties by looking at the marginal revenue function as well. But of course, revenue is only one side of your balance sheet. We don't want to maximize sales revenue. We want to maximize the amount of money that's left in our pockets after we have sold and also paid to produce that quantity. In other words, we want to maximize profit, not revenue. And that requires considering the other side of the ledger, which is the cost, the total cost function. And so decision report 4 is the big meatball for this project, is that we have to balance revenue and cost to figure out how to maximize the profit, which is the difference between the two. So the profit, a little hard to see on the screen here, maybe I can zoom in on it some. Profit is nothing more than the difference, the vertical distance between my revenue function and my cost function, right? It's the revenue minus cost. How much is left in my pocket after I have paid to produce as many units as I would need to sell in order to make that amount of sales revenue. Revenue minus cost gives me profit, and that is what I'm trying to maximize. And so in this fourth and probably most important fundamental decision report, we want to figure out how to make that difference between revenue and cost as large as possible. And in this little visual, it looks like that difference is maximized right about here, right? The largest vertical line I can draw in between my revenue function and my cost function is right about there. And that's a place at which the slope of my revenue graph is exactly the same as the slope of my cost graph. So the place where we maximize the difference between two functions is going to be a place where the slopes of those two functions agree with one another. That happens because when I take their difference, when I subtract them out, the slope of the difference between those two functions is going to be 0 at that point. And that comports with our understanding of how to find the maximum or minimum values of a function, find the places where its slope, its derivative, is equal to 0. And so if I want to know where the derivative of my profit function is 0, I'm really asking, where are the derivatives of my revenue and cost functions equal to each other? Okay. So when you see optimization for profit in your other management science textbooks and stuff, it usually appears like this. We're going to maximize profit where the marginal revenue and the marginal cost are the same, are equal to one another. That's going to be a place at which, if I produce just one more unit of my product, I will make exactly as much by selling that product as it cost me to make that product. Right? And that's the sweet spot. That's how we know that we're at the top of the profit mountain, when the marginal revenue and the marginal cost agree with one another, which is the same as where the marginal profit, the derivative of the profit function, is equal to 0, because that's where we find the maximum and minimum points of a function. So the big idea of decision report 4 is going to be to find that point, or potentially points. There might be more than one, depending on how your cost function is structured. Where does marginal revenue agree with marginal cost? And then finally, this is sort of the overtime part of the project. Once I decide on what price I'm going to set and how much quantity I'm going to sell, let's suppose I'm going to sell my product for $292.96 and I'm going to sell 750,000 units per year. So I've set my price, my quantity. I determined that that's my optimal profit in decision report number 4. There's still a bunch of money that gets left on the table. And it gets left on the table because there were a bunch of consumers that would have been willing to pay more for our product than we ended up deciding to charge them, right? There were still people who would have bought at $330, would have bought at, $447. There were still people who were willing to pay more than $500 for my product. Not that many, but they're out there, right? And so once we decide on a price, we are foregoing a bunch of additional potential revenue out there that's generated by those people who would have paid more. We can quantify that amount of lost revenue as something called consumer surplus. It's the orange shaded area on this graph. If everybody in the whole national market was able to pay their maximum price, whatever my highest amount is in my brain that I would pay for the product, if everybody paid their own maximum price, we would not only make this green amount of revenue, but we would also make this orange amount of additional revenue that comes from some people paying more than others, right? That total orange amount is called the consumer surplus. It's the amount of money we leave on the table because there were people that are buying our product who would have paid more for it. And so one of the ways to dip into that consumer surplus is to implement price discrimination schemes. We see this happening, for example, if you just drive across the Sagamore Bridge, which is just next door to me over here, the price for gas immediately goes up by about 20 cents as soon as you cross the Sagamore Bridge onto Cape Cod. Because in Cape Cod markets for gasoline, there are people that are willing to pay more. And so gas companies, oil companies do what's called price discrimination. They charge more for the same product in different markets versus other markets. And that is how we can dip into that consumer surplus and reclaim some of this orange area as realized sales revenue. And so what I'm asking you to do in the last decision report is just to come up with 1 or 2 potential price discrimination schemes that can get us some of this additional sales revenue that dips into the consumer surplus, and also to determine how much is the total amount of consumer surplus. What's the most amount of money we could make if we practiced perfect price discrimination, where every consumer pays their own maximum price for it. And that, as you might expect, because it's an area underneath this curvy demand function, that is computed with a definite integral of the type that we were introduced to today. So that is the overall shape of the project. We start from this very sparse set of test marketing data for your product. We scale up each of those test market data points to a predicted national market demand, right? Just by scaling it up to the large size of the national market, which your data file will have that information for you. We use those data points to determine our demand function. This is the star of the show, really. The quadratic function which best models the relationship between price and quantity that we saw from the national market demand. Once we have that, we use it to determine a revenue function, just by multiplying my demand function by Q. Those revenues can also be thought of as the areas of these rectangles on the demand graph. With your revenue function in hand, you then also need to determine how to maximize the profit, which is the difference between revenue and cost. And profit gets maximized at the place where the revenue and cost functions have the same slope, where marginal revenue and marginal cost agree with one another. You'll find 1 or more potential places at which profit is maximized in decision report number 4. And then in step number 5, figure out how much money is still potentially out there on the table that consumers would have been willing to pay more for your product. What's the total consumer surplus? And come up with a couple of price discrimination schemes that could help you to dip into that consumer surplus by charging some consumers in some markets more than you charge in other markets.